Okay, welcome everybody. And right now I want to talk about the existence of derivatives. So remember, let's recap just for fun that we're saying that given any function, let me zoom in a little bit for the kids at home. So given any function f, then the derivative is given by, so I'm going to put up here the derivative, f prime of x is given by the limit as, now I'm doing this because Joe doesn't like it. Joe likes h's instead, and so does Hannah, so I'm purposely going to keep using delta x's now, just to bug them. So, if the limit exists, it's now time to talk about that statement. If the limit exists. Okay? It's now time to talk about this. And we do understand that this is a new function. And what this new function gives you is the slope of the tangent to f of x for any value of x.
So you put an H on the bottom.
Yeah. Oh! Delta x, ha ha ha, for any value of x on the domain of f. And we're going to talk a little bit more about that tomorrow after you've practiced your algebra a bit more. So, the existence of derivatives is what I want to talk about right now. So, a function f is said to be differentiable at x equals a if f prime of a exists. At points where f is not differentiable, we say the derivative does not exist. There are three common ways a derivative can fail. These are three common ways a derivative can fail to exist. And you're going to do a diagram. We're going to do 4 diagrams, actually. The first one will look like this. And the function f will do something like that. So the function comes to a little pointy point here. And that actually is called a cusp. And we'll draw another one. And this would be, for example, maybe we have a function f that comes like that, and then it goes like this. So it's piecewise linear. But it's creating what we call a corner or a kink. Depends on... Oh, absolutely. Better? Okay. Did I spell corner wrong? C-O-R-N? No, it's a corner, and I've actually seen it called a kink. Little kink in the graph. I don't know. Call it what you want. Corner or a kink. And that would be at a given point of A. Another example of how a function could fail might be this. So all of these, I'm looking at a point here, A. I'm looking at a point here at A. I'm looking at a point here at x equals A. And that one's called a vertical tangent. And the last one that I think that we'll talk about, and again, this is just a generalization. They can look very different, but they'll have the same characteristics, is maybe where the function I don't know. How's that grab you? Where it's discontinuous at x equals A. So I'll give you a chance to copy that down. Kids at school are copying it down. Okay. And we're going to talk a little bit about why the derivative does not exist at those points. And I'm going to post 2 videos below this video on the LMS that both the in-class group is going to watch at home and the group at home is going to watch, because they do a really good job of it, and it's going to save us some time. But in general, what we can look at here are some reasons why some of these might not exist. If you think about the limit coming to a cusp, if you think about the right-hand limit and the left-hand limit, because remember, this is what we want. We want the limit as x approaches 0 for any point. I'm looking at an A value, so I guess I should make that point. So at this point, we're seeing if this exists. We're seeing, I'll use h's just so I don't make a mistake like I did before. That was so embarrassing. Thank you, Joseph. He caught me. So it's a plus h minus f of a over h. So we're looking at places where this exists. And if we think about this, that should be an A. No, that shouldn't be an A. So we're looking as we're approaching A, right? And this is approaching A from both the left and the right. So that's coming closer and closer and closer to this. And we'll notice that the derivative on this side, or the limit on this side, is negative at least, right? And the limit on the other side is positive. And they're always going to keep going and going and going closer to infinity. So you notice that at this cusp, the limit does not exist. So this limit cannot exist at that pointy point. So the limit does not exist. And again, you're going to watch the video and they're going to talk about that in more detail. If we look at this one, if I'm coming from the left-hand side of A, you'll see that my slope of the tangent is coming off that way. And if I'm coming from, well, yeah, this is just not good at all. That's just a bad, let's change that kink. See what I did? That's not a function. F is not a function. It's a relation. That should be bent that way. Silly me. Let's bend it that way. Otherwise, it's a relation. It's not a function at all. And that's a different conversation. That's completely. So there's my kink, or my corner, and you'll see that my two slopes of the tangents aren't matching up, are they? So that derivative doesn't exist because the limit doesn't exist. So this limit doesn't exist. This one, as I approach from the right and as I approach from the left, the limit is approaching infinity. So the limit doesn't exist. But there is a vertical tangent line there. There's a vertical tangent, and you know that that's going to have an undefined slope. But you know that if this is going to represent the slope of the tangent at A, this is the slope of the tangent of f of x at A, well, it's got to be a finite value, right? If it's going to be a limit. Limits have to approach a real number. And infinity is not a real number. So that derivative does not exist because the limit does not exist again. Although there is a vertical tangent line there. And this one, you can tell that the limit does not exist once again. And this limit does not exist. For all the reasons discussed. And again, there's 2 videos below that you're going to watch that'll take you through that in a little bit more detail. So I've got a summary for you. Oh, got some people copying it down, which is good. I'll just hold on a second. Yep. So I've got a summary. The derivative of any function f at A exists only when the tangent line to f at x equals A exists and has a finite value, which means a real number value, a real number value. Not infinity. So if we go back to the pictures that we had, you'll see that we have some problems creating that tangent line. We do have a tangent line here, but it's not a finite value. We can't get a tangent line simply here. We have problems creating this tangent line here, depending if I go from the left and the right, and the same issue here. So that takes us to a theorem. If f is continuous, nope, sorry, if f is differentiable at A, so this is if f is differentiable at A, then, so it's a very powerful if-then statement, then f is continuous at x equals A. So if f is differentiable at A, then f is continuous at A. Now, let's talk about the contrapositive of that statement. You've never heard of that probably before. It's a logic statement. It's used in math. The contrapositive statement to this if-then is if f is not continuous, at x equals a, then, there's your if, then f is not differentiable. At a. That's called the contrapositive to this statement. And it happens that the contrapositive to this statement is true. Now there's something called the converse of the statement. Now this is how the converse of the statement goes. The converse takes this if and then and reverses the direction. It says if f is continuous at x equals a, then, so the converse, if I start with f being continuous, then f is differentiable. At a. That's called the converse of the statement. And the converse of the statement is false. So what that means is, it means continuity is a necessity for differentiability. But not a sufficient one.
Sir, we can't see.
There you go.
Sometimes.
So continuity is a necessity for differentiability, but not a sufficient one. So just being continuous does not mean that you can be differentiable. However, you cannot be differentiable unless you're continuous. So you have to be continuous to be differentiable, but it's not good enough. You have to be continuous to be differentiable, but it's not good enough to be differentiable. So here's an example in your life. You have to be a BT student to be in this class. Yes? You have to be a BT student to be in this class. But just being a BT student doesn't put you in this class. That's the way that works. So let's take a look at an example that we'll do together. We'll draw it. So let's put a dot here. Let's put a open dot up there. Let's put a open dot here. Let's go up to there. Let's take off like that. Let's put a vertical tangent in here. And let's come down, and let's take off, and let's put this one here. And the question, one of the questions is going to be, at what points or at what values of x on -2 to 4 is f of x differentiable? And then I'm going to compare that to at what values of x on -2 to 4 is f of x continuous? The first thing to make note of here, maybe I can make it bigger. Looks like Joe is squinting at the back. How's that, Joe?
Perfect.
Okay. I'll give you guys a chance to copy that down. Maybe I'll pause the video here and I'll come right back.